All right. So, as I said before, when looking at star death, the physics that guides us is the Pauli exclusion principle and the Heisenberg uncertainty principle. Okay, so let's go over those very quickly. We're going to go back to, we're going to just look at a whiteboard so we can talk about them. Now, remember, we'll talk about the uncertainty first. All right, I'll write it here. Heisenberg uncertainty. I know I'm spelling uncertainty principle. I probably misspelled uncertainty, but you know, what are you going to do? I was not hired for my spelling abilities, to say the least. So, so if we look here, the basic way we look at this is delta x, delta p is greater than or equal to h. I think it's h over 2, but as my PhD advisor said, the universe is correct to a factor of pi h bar or 2, and this has both of those. So I think it actually is h over 2, but I never have these little details memorized. So anyway, let's talk about what this means, because the meaning, whether it's h bar over 2, doesn't change the meaning of the principle. All right, so let's talk about each term. You have uncertainty in position. Actually, I'm not gonna write those out because, as I think you may have figured out, I really can't spell uncertainty. And so we have our we'll just do this the old-fashioned way. We have our uncertainty in position here, and our uncertainty in momentum here. All right. Now, what Heisenberg's what this says, this uncertainty, is that you can't know both of these simultaneously. If you could know delta x and delta p simultaneously, then this would be 0. That's what that would mean. That would mean you could know both of these perfectly. What this says is that there will always exist some uncertainty in momentum or position. And it also says that as one way to understand this is that as delta x increases, right, delta p will decrease, will go down, and conversely, if delta x decreases, that is, goes down, delta p will increase. So another way to look at that is as your position, your uncertainty in position increases, your uncertainty in momentum must decrease, all right, and vice versa. And so what we can see here is that if we looked at neutron stars or white dwarfs, and neutron stars, we find for both of these, as the mass increases, as mass goes up, delta x gets smaller. Okay, and we saw that, and we can see that whatchamacallit, that as it gets smaller, delta p increases. Hold on. Okay? Now, with that being said, we'll look at this for a minute, go to our next board. So, but what we know from general relativity, or not general, or actually all special and general relativity from Einstein, we know that delta P max, there's a maximum delta P occurs when the velocity implied by delta P is equal to c, the speed of light. All right. What the theory of relativity tells us is that there is this ultimate speed limit to the universe. All right. Now, so the Heisenberg uncertainty principle, because things get more massive as they get smaller, then or the gravity pulls down on them, more. Basically, as the spheres get smaller and smaller and smaller and smaller and smaller, you up the velocity of the particles inside. And when they reach the speed of light, that's it. And that gives white dwarfs and neutron stars a mass limit. Okay? So we saw in the slides last week what those were. It's about 1.4 solar masses for a white dwarf, and I think about 2.5 solar masses for a neutron star. And anything else has no physics to explain it. But in order for that sentence to make sense, we need to understand the physics that explains white dwarfs and neutron stars. And this is the Pauli exclusion principle. Fun story. So I had a family call for Mother's Day. I got kicked out. It's the stupid button on this pencil. I mean, I realize it's supposed to be convenient, but it's anything but. So anyway, as I was saying, I was on a Mother's Day Zoom call with my cousins, my aunt and uncle, and my mom. And my cousin told me that on her mom's side, not the side of the family I'm related to, they actually found that she is a cousin of Wolfgang Pauli, who the Pauli exclusion principle is named after. And they asked if I knew who that was. And I said, not only do I know who that is, but we are talking about them. We are talking about him in astronomy today and have been for the last couple weeks. So that was kind of exciting. So they asked me if he was important. And I said yes, and explained to them why. So the Pauli exclusion principle is what we called degeneracy pressure. All right, and if you remember, we talked about seats where electrons could live in these energy levels, and we can only have one electron in one quantum state. Each energy level allows for spin up and spin down, which are different energy levels. So quantum unique states can only have one energy level in them, and this applies to types of This attaches to quantities that have been classified called fermions, which means that their magnetic spin is not a whole integer. It's a half integer, or a fractional integer, like 1/2 or 1/3. What this basically means is that as gravity pulls these things down, like in a white dwarf star, electrons start to stack in these quantum levels. Okay? And they stack one by one, filling each quantum level up until there's no more. And the more quantum levels it can fill up, the more gravity is pushing, but gravity gets to a point where it can't overcome this this degeneracy pressure, or the Pauli exclusion principle. Now, we talked about this in terms of movie theater seats, right? If we took our class and went into a movie theater, there would be, you know, a lot of empty seats and a lot of ways we could arrange ourselves, right? But if there were only 13 seats, it would get much tighter, right? Everyone would have just one seat. And if you start taking away chairs, things could get, you know, things get interesting. You have musical chairs. Now, that being said, whatchamacallit, so in white dwarfs, we saw that electrons, you know, the electrons get pushed into these quantum levels, or gravity pushes them in and fills up those quantum levels, which you think of as chairs. Now, if a star is massive enough, all right, then you can actually drive the protons and electrons into each other and create neutrons. And neutrons obey the same rules, but you create a lot more chairs, and they're a lot closer together. Right? They have a different distribution of chairs, if you will. All right, so there can be much bigger and fill up these levels and withstand the extreme conditions of a neutron star. All right, but they still have a mass limit based on relativity, right, and the Heisenberg uncertainty principle. Now, if you know, when we ask ourselves, how do we know black holes exist? Because we have compact dead star objects that don't emit light, right? That don't have the properties of neutron stars, like they don't act as those pulsars, and they're much heavier than the neutron star limit. So why we call them black for two reasons. One, because the escape velocity predicted by physics is greater than that of light. And two, we don't have physics that describes them. We just don't know what's going on in there. Yeah. Question?
Is it true that they actually seen with telescopes black holes already?
Right. So that's a good question.
They've
so
been discovered. I mean, they've actually seen one.
Right. So what they were able to do is process the image and create an image of a black hole from a telescope. Because even though the black hole itself, no light can escape from it, you can see light and things going around. You can see light that will be heated up matter outside the black hole's event horizon, and we'll talk about what that means later. But yes, it happened just this year actually that a picture of a black hole was found. I'll probably
also, I heard there's one around not so far from our.
Well, that's just a possible explanation of strange motions in the Kuiper belt.
Oh, okay.
So it's a possibility for sure, and it would actually be kind of cool if it was there, because a small black hole like that, if found, could actually be used as a power source for a lot of interesting, you know, applications, because it's thought to move into a more advanced civilization. One has to be able to create a small black hole for a power source. So if we already have one in the solar system, that would be incredibly useful. But
oh, that's cool.
But that being said, it's one of many explanations, and it's not, you know, it's one of those things that needs that needs confirmation, right?
Oh, okay.
So there's a bunch of explanations for the strange orbits in the Kuiper belt. And a black hole is not considered to be one of the more likely explanations, but until all those orbits can be explained, it's possible. So yeah, no, those are legitimate things. And one of the reasons to launch telescopes is to actually solve that mystery. Because like I said, if it is a black hole and we can find it, that would be an extraordinarily
Do you
useful
think
thing.
James Webb telescope might be able to handle that task?
It might, because James Webb isn't designed for visible light. It's designed for infrared light. And there's a lot more to see and a lot less scattering in infrared. A lot more light just goes directly through things. So it might be possible with James Webb to find ultra hot matter in very small places in the Kuiper belt over very small areas, whereas we wouldn't see it visibly because it would get scattered by anything it came in contact with. It's sort of like imagine if you had a flashlight, right? And so say we wanted to talk from LaGuardia, to my house. You can see the World Trade Center from both places, so there's some line of sight there. But a flashlight's going to scatter. But an infrared beam, if it's bright enough, if it's really intense, I should be able to see it. Should pass right through all the buildings and everything. So that's what James Webb might be able to do. And if you see a super hot, right, very hot, but very small compact source, which you couldn't see with any other telescope now, then you could that would be evidence for a black hole, right? So I think James Webb would be able to help us with that. And then what would be fun is the hypothetical structures to leverage a black hole for power would also be pretty cool. So yeah, that's it would be interesting if there was one. But like I said, there's competing theories and explanations, and they just have to be borne out. That's all. So let's go back to. Let's get to the black holes. Let's see, sharing a file. So, so here's what I don't like, and I explained this last time, right? We saw here the white dwarf limit, about 1.3 solar masses. We went down to neutron stars, I believe. We saw colliding neutron stars. Did it give us it? Yeah. And then we saw that the neutron star limit is about 3 solar masses, which you can see here. And then we get to black holes. Now, it tells you a lot about black holes, but I don't like this picture because it says, what is a black hole? And it says the curvature of space-time becomes greater and greater as we approach a black hole, and the black hole itself is a bottomless pit in space-time. All right? So if we want to understand, sure, you could tell someone that and parrot it, but it doesn't help us understand in terms of reality what's going on with a black hole and why exactly they are so strange. And it also overlooks understanding that the universe, the best experiments we have about the universe to describe the universe we live in, do not conform with our intuitive nature of reality. So what I want to do is, or what I've been doing is sort of having this video general relativity thing, and I'm going to ask you to we're going to think of it as an activity, and we're going to do the activity at the front end of class instead of at the end of class. And so I'm gonna talk between each video, so don't check out for too long. And each video's difficulty on a scale from 1 to 5 is a 5. So we're going to need to explore each one. That being said, it's our goal. The goal of this is for you to understand how to construct a simple experiment that can pit Newton's laws of motion, which are pretty intuitive to most of you at this point, and Einstein's general theory of relativity as a picture, and understand why the experiment comes squarely down on the side of Einstein and not Newton. Because understanding that experiment, the experiment itself is actually very simple and straightforward. All you need is a mirror, a laser, and actually, no, you don't even need a mirror. You just need a laser and and 2 sensitive detectors. That's it, and a stopwatch. So, so if you make the stopwatch an atomic clock, it's easy to do. So, we want to understand why people conclude the universe looks this way. And I want you to understand this because I have a fear as a physicist and a scientist that a lot of people think that this is sort of a mental exercise and that it's just sort of said to sound confusing, and B, people think, okay, that's nice and that's a fun idea, but that's doesn't really explain anything. Why are we doing this? And so my hope is that you start to understand that general relativity is more explanative than Newton's laws. And in fact, we need to understand general relativity to make things like global positioning services work. GPS needs it, and a lot of motion for sensitive sensing from space relies on general relativity being correct. If general relativity did not exist and weren't true, your GPS would not be more accurate than about 100 meters or so. And because of general relativity, it allows us to get the precision down to about 6 meters, or 2 meters or 3 meters. So let's go and start this. So what I'm going to do is I'm going to link the videos in the order we want to watch them, and I'll sort of say go, and then I'll add a couple minutes on, and we'll check back in and talk about the videos. And then after we've done, we'll sort of discuss each one. And then after we're done with that, we will we'll have a discussion. And then what you're going to do is pretend it's an experiment we've done, like the telescope or the first one we did. I don't even remember what it was. The phases of the moon, and it's an activity. Just write about what I'm interested in learning is what it's like for you to learn about general relativity and how it's changing the way you look at the universe. And so you can use your guidelines to answer that one main question, right? So that's what I want to do. I expect it to be hard, so I want you to write about that struggle and about what it makes you think about. I think that'll be interesting because I've been thinking about general relativity for a very long time, and I get lost. I have what I think are revelations about the universe, and then I go, oh no, that's not true. So I'm hoping that it's at least a little fascinating for you too. So with that being said, in order to understand black holes, we need to understand what space-time is. There is no context in this or most other books for space-time. They just expect you to accept it and think of it as magic. So what I'm going to do now is I'm going to post a link to the first video. Hold on, our space and time. All right, there we go. All right, I did it. I did it in the right order. So, okay, so let me go to the chat room and okay, so click that link and watch the video, and we'll check in about 13 or 14 minutes. So about 3. So it's 3:50. So at about 4:04, I'll come back. I'm going to turn because I want to watch the video too. I'm going to turn my stuff off or my audio off. I'll leave my video on so you can all watch the video, and then we'll be back then. So hop to it, and we will discuss. All right. Yeah, no, I'm back. Can you hear me now? It's 4:04. So, oh, okay. Yeah, no, I was once I finished the video, I was looking at stuff from my server. Um, so, okay. So a lot of hard stuff to look at there, but you can see that space-time, I'm hoping that, so goals of that video, I hope you see that it's a lot more complicated than, oh, it's space-time, it's just some 4D thing I can't picture. So if you'll recall from the video, he talked about some things he just asked you to accept, such as about the order of events and distances and things like that. And I can tell you that that stuff can be experimentally verified, particularly in the analysis of cosmology and things like that. But we can view length contractions, time dilations, and things like that in the lab. And in fact, special relativity, which is the basis for a lot of that, those conclusions, they're a consequence of that statement of the speed of light being constant in all reference frames. So I want to talk a little bit about what that means, because that's something that's said a lot, but is not really understood, right? If I asked you all, is the speed of light constant in all reference frames, a lot of you have probably heard that. And since Albert Einstein said it, you probably accept it as true, but you got to think about what it means, right? So I have a simple example I like to talk about that involves students throwing water balloons at me. So imagine you had a water balloon cannon that fires a water balloon at 20 miles per hour, right? So the speed the water balloon hits me at is 20 miles per hour. Now imagine you were in a Jeep coming towards me at, say, 50 miles per hour, like a truck, and then you fired the cannon. So if you're on the Jeep if you're moving at 50 miles per hour and you fire something that gets another 20 miles per hour, it hits me at 50 plus 20 is 70 miles per hour. Now, here's what it means for the speed of light to be constant in all reference frames. If instead of a water balloon cannon, we have a laser gun, right? When you fire the laser gun at me, if you just fire it at me standing there, I would measure the light moving at the speed of light. If you're moving at the 50 miles per hour, I'd still measure it at the speed of light. It wouldn't be the speed of light plus 50. And you might be thinking to yourself, well, the speed of light is huge. Of course it wouldn't be. You've already said that before, Professor Toland. $100 plus a penny is still $100. That's true, but say you were moving at a spaceship moving at half the speed of light, right? And then you fired the laser, I would still measure it coming at me at the speed of light, not 1.5 the speed of light. So this fact that the speed of light is constant in all reference frame leads to these very counterintuitive conclusions. If that speed must remain constant, right, and speed is in meters per second, then the meters and the seconds that make up that speed of light have to change so relative to the perspective you're measuring in, so that that speed can remain constant. All right? And so what does that have to do with causality or understanding causality? Well, things can be causally connected if they're within a distance in which light can interact with the other one. All right? And if two things are so far apart or moving far enough apart from each other at a great enough speed that light will never catch up to the other object, they're no longer causally connected. All right, so that's what he means by the influence there. Looking at the space-time diagram, that space-time interval is a tough concept. It's a distance in 4D space-time. So we can, we'll see more about it as we go through the video. But yeah, I don't know. Any other thoughts about the video? Feel free to ask questions or pick up on anything. I think while you're typing or just feel free to interrupt me too. I think what my favorite part of that video, or the most mind-blowing part for me, is understanding that space-time is not a dynamic quantity. So we experience what we mean by that. I want to expand on that and talk about it maybe a little slower. Yeah, Margarito.
So we experience time in a linear way, right? Like when we see time and we think of hours, days, and weeks, right?
Well, that's sort of what I was getting to. The space-time is not this kind of space or this kind of time. like how we talk about linear time versus circular time philosophically, it's a very different evolutionary concept. In space-time, to reiterate what he said, in a space-time, in a Minkowski space-time, there is no evolution. It just is. So time isn't linear, it just exists.
So we
Right?
still, so it's like our future already happened, our past already happened, right?
Sort of. I mean, that's the right way to start looking at it, because that breaks you from the normal way of thinking about things. Remember, that's the first thing he said. A more correct way to think of it is probably that your future and past just exist, and that there's no real difference between the past. Your past already happened, your future already happened, your present already happened. Your existence is an object in the universe, a collection of events, space-time events. It has a beginning and an end, and everything in between. And that's it. It's sort of that's a more correct way to think of it. Sort of like this is an object in space, right? Without being an object in time, without putting time in there, it's just an object. Without time, it will occupy these coordinates. Then it will not occupy these coordinates, and that's it. So it's in some ways it's even worse than it's already happened. It's you're just an object in this 4D space time, and that's it, right?
So it just exists.
Right. We exist in this 4D space time. And I like that he was willing to say, and he did address that, why do we perceive the existence the way we do, right? In this kind of space and linear time as we see it, nobody really knows. I mean, that's a question. I think that's one of the questions that if you spend some portion of your life thinking about, I'll feel like I did a really good job teaching you. It's certainly what draws me to this subject. I think a lot of times, especially since we're not majoring in science, we wonder, why do I have to learn about science in college? And I think learning to think about things like these and understanding that there is a rigorous way to look at these questions in the natural world is really fascinating. It's up to you, of course, to apply the context in which you do it. But if you want to stick with science, though, you'll probably find you become a science major. But there's no answer to why we perceive it the way we do. There's no good answer for that. We just know we do, right? We all kind of agree on what a day is, and we can make experiments that help us understand the nature of reality that are repeatable by other people. And I often say that in my physics classes particularly, that physics will tell you a lot about how something works, but it doesn't tell you a lot about why something works, right? So it can tell you how reality works, but it won't tell you why it works that way, like why you perceive it that way. And even still, physics runs into its limits. There's still big unanswered questions in physics. Physics is not a complete subject. It's not a finished work by any means. So I guess I know it's an unsatisfactory answer, and I think we'll have a lot of those, but it's something to think about for really the rest of your life. It drives me crazy sometimes. Any other questions, or should we move on to the next video? All right, hold on. I'm going to copy and paste the link. Let me go back. Okay. All right. So we'll come back at around, let me see how long this one is. So this one's 12:32. So that you'll notice there's comments at the end of a lot of them. At all of them, you don't need to watch the comments. So let's say this one's probably 10 minutes. So let's say at 4:28 or 4:29, we'll come back and discuss the Is Gravity an Illusion episode. That's what you should have up. Okay? So I'm going to turn off my mic and we'll get it started. Yes, watch the video. most of you should be wrapping up. I'll give you another minute. Okay, so with that video, that should give you some context. Now that we sort of, the first video we defined space-time, but now we can sort of see what Newton was saying about forces and gravity and what Einstein started to say, right? And they introduced the principle of equivalence, which is that you can't tell the difference in a free fall frame, then that's indistinguishable with a gravitational field than being in an intergalactic faraway frame without gravity, right? But the same criteria for those inertial frames are mentioned. So so we also alluded to what he's going to build up, because what things we haven't built up is what does it mean to be straight and what does it mean to be curved. If I asked you all what it means to be a straight line, you'll say, oh, well, it's the shortest distance between 2 points. Well, remember, we're not talking about this kind of space or this kind of time. And in a flat geometry, your Math 115 or Math 200 explanation is perfectly adequate. But he just talked about curved and non-flat geometries. And so there, we're going to find that we have, a different definition there. And what we're also going to have to find is that, our definitions of straight are going to have to be revised, and our definitions of curved are going to have to be redefined too. So, but you're going to find that the definitions are similar to what you think, but you have to put them in the context of a 4D spacetime. And there's going to be a tool that's developed over the next 2 videos called the spacetime diagram, and that will help us keep track of everything. It will help us bookkeep, but it will not give us a picture, all right? So when we look at pictures like this, and you're going to hear the presenter, Gabe, say this a couple times, pictures like this are not meant to actually visualize the black hole, right? They're meant to sort of divorce you and say it's not this kind of space, and it's not this kind of time. But you could start to see the, what's meant by relative motion, right, with the train example, measuring from inside the train versus measuring from outside the train, and that definition of an inertial frame. And, that's important. Again, just seeing that those are 2 things, different things. And then what Einstein is going to do is he's going to reconcile, or he's going to come up with this new way of explaining things. But you might be wondering, why come up with a new way to begin with? Like, was Einstein just being one thing that they don't talk about here is, why was Einstein, why would you come up with this new theory of relativity when gravity works? And yes, there was a lot of impressive genius with Einstein. I'm not denying that. But there were questions. Galilean relativity by the 1900s, by the early 1900s, did not work anymore. And it didn't work with electricity and magnetism, which was the crowning theory of the 19th century. And what I mean by that is, if you imagine a charged ball, right, say on the tip of my pen, moving charges give you magnetic fields. Now, if I am standing still, say you're in a train with me and you have a compass, your compass, as long as we're moving in the train, is not going to register a magnetic field. But if you're outside, your compass will react to that charge passing by, and there'll be a magnetic field. So it's sort of easy when you're looking at frames to say, oh, well, they're both right, there's a relative transformation, but frames agree, right? So what I mean by that is we might disagree on the path of an object. So sitting in the train, you might see something go up and down, and you might see it go like this if you're outside the train through the screen. Let me try and do it up and down through the screen. However, the object always leaves my hand and ends up in my hand, right? There are these coincidences. Now, that being said, in this example we're talking about with the charged particle, is there a magnetic field or isn't there? One person can measure it, one person can't. And Galilean relativity did not answer this question satisfactorily. And Maxwell's equations were inconsistent with Galilean relativity. And in fact, a guy named Lorentz created the correct relativistic equations, or frame-changing equations, for what became Einstein's theory of relativity. But he couldn't accept the conclusions, the physical theoretical conclusions that his math were implying. And that's often the case sometimes, and mathematicians get confused, whereas Einstein didn't come up with that math, but he certainly gave it physical context and created a broad view of the universe with it. Lorentz came up with the math, but couldn't see the implications of it. This is a sort of a common story that happens frequently in physics. So it's important to note that relativity wasn't working. There needed to be a way to make electromagnetism consistent between frames, to create an inertial frame, right, to understand the frame. And part of that was understanding with the Lorentz force. That's why the Lorentz transformations were invented. The Lorentz force looks at magnetic fields and electric fields as two parts of the same phenomenon, and it combines them into what we call electromagnetic theory. And that creates the physical explanation that says, oh, well, an electromagnetic field can have an electric direction and a magnetic direction, and sometimes the field's all electric, sometimes it's all magnetic, but it's the exact same as being a little bit in a positive direction or a horizontal direction and a little bit in a vertical direction, right? So if you make some sort of, I'll try and draw it on here. I should probably be taking advantage of my pencil. So you can look at it like this. If you have a coordinate system, you have x and y, you can write a vector here. It's a little bit of x and a little bit of y, right? So it'll have x and y components. You make a triangle to sort of look at those. You can do the same thing with electromagnetic phenomenon. You can have an electric field direction and a magnetic field direction. And an object in this context has a little bit of E and a little bit of B, but there's nothing stopping, if you can picture it rotating, sort of rotating in a circle. There will be times where it's all electric and times where it's all magnetic, if you look at it from a certain way. And this allowed it to be reconciled with the Lorentz transformations, which turned out to be the correct transformations for Einstein's relativity, and then made electromagnetism all of a sudden work like a classical theory should. So there's definitely a huge motivation for working on this problem. It doesn't just come from nowhere. That being said, we learned a little bit about from what Newton says about how objects work in a gravitational field, and we learned a little bit about how Einstein's picture would change that. But as we saw, there was that pretty convincing experiment, right, where two objects will start to go towards each other. That looks like a pretty big win for Newton, but we alluded to a fact that Einstein can use a loophole to get out of it. So in order to understand that loophole and to be able to develop an experiment to see if Einstein is right or Newton is right, we have to understand how to analyze events in space-time. And that's what we're going to spend the next video and the one after that doing, I believe. Yeah, there's So I think we're building up in the next two to the space-time diagram and straight lines and curve and what it means to be straight in a more general definition. Okay. Before we start the video, though, there's something I do want to talk about. So the only mathematical terms we need to know are parallel, right? So if two lines are parallel, do they ever cross? That's my question to you. No, right? That is fundamentally the most advanced mathematical feature we'll need here, is that parallel lines don't cross. The other is, you're probably not familiar, is transport. When I'm transporting something along a curve, I'm moving it. So if I wanted to transport along this circle, that means to move along the circle. That's it. It's very straightforward. We all know what the word transport means, right? So if I'm going to parallel transport something, that means, because he's going to talk about that, and that's going to seem like an advanced topic, and it's really not. So if I'm going to parallel transport something, that means that I'm going to orientate it along the curve when I start, and I'm going to move it along the curve. All right, so if you can imagine this arrow, actually you don't have to imagine. If I transport this this arrow, or at least this part of it, I can move it along the curve, right? So it's parallel transport if I start parallel to the curve and then move it along that curve, and I just start out parallel. All right. Now you'll notice that in a straight line like this, you'll notice that I'm always facing the curve. But let's look at another situation of this. All right. Let's make that line. We'll make it to this curve here. Hold on. So we've got a curve like this. Now if we move this curve along the circle, you'll notice our direction changes as we're at different points along the circle, right? And our direction relative to the curve will change from this curve, right? So we have to get around. Oh, now it's rotating. That's not helpful. As we get back, and then eventually we'll get back to it being on this line, right? So that's what we mean by transporting and parallel transporting. And so those are topics that will come up in the next video. So are there any questions on the last video? Then let's watch the next one, and we will reconvene in about 15 minutes. So 4:40. So let's see here. What time is it now? It's 4:40. So let's say 4:55. Okay. And there's the link. Forgot to do the link. Okay. Okie dokie. So I think, as Katya pointed out, this one is a little easier to understand because it's just math. But again, I want to point out that everything we're watching is very connected and important to understanding the bigger picture. Now, don't freak out if you're not understanding the bigger picture. I actually recommend that you sort of bookmark all of these videos and maybe watch them again. Maybe watch them with one of your little siblings or your parents or something and talk about them afterwards, what you think things mean, what you think other things mean. I have watched these videos probably 20 times and I've yet to be really bored by them. So this set of videos. So yeah, you'll want to, you'll want to marinate with them. Don't worry about having everything click like this. It's really one of the hardest topics out there. And again, he pointed out, I think it was in the last video, that you need that 1,200-page book, which I have in my office on gravitation. It's been one of my life goals to try and find the time to get through that book. I'm kind of hoping once I have a lot more time for stuff like that after I finish all my promotions and things like that. My specialty, again, is in quantum physics, which is the physics of the very small. It's very discrete, whereas this is general relativity, is the complete opposite, so I'd like to learn about it. Any questions or thoughts about this video? Were the ideas of straight and curvature, the whole parallel transport and tangent, clear in the video? Does anyone have any questions? It is an interesting theory, but remember, it's an interesting. No, not if whether the Earth is flat or round. Not happening at all here. We're talking about the space-time the Earth exists in. The Earth itself is in our three-dimensional space. The way we look at it is round. Is the space-time? How does the space-time in the Earth exists in? What is the shape of that? Of the geometry? Flat space-time would not indicate that you can prove using this definition of flat that the Earth is indeed very simply is curved, because again they talked about the topology versus the geometry. So let me make that clear, because I think I see what I'm seeing here. So you can actually describe a perfect sphere in just 2 dimensions. All you need are the 2 angles theta and phi, and you get everything. You don't need any of the radius. Now with the Earth, proving, with something like this, you can show, again, very clearly mathematically that even though the ant will always see it flat, right, or a person, if you walk around the whole Earth, you can prove that the lines close in on themselves and that the Earth is topologically round. So in that sense, where you talk about the connectedness of the points, you need to be, if you're going to talk mathematically, you must be mathematically rigorous. You can't be Floydy about it, or sound cool at a party. Although I saw one of the comments said you could say this stuff and sound cool at a party, and it says, what party is that? I guess that's a good point. But you need to you just have to understand these things. They need marination, and they need to be said in the right context with each other. And I do want to remind you again that gravity is an interesting theory, but it's a theory in the scientific sense, that there are thousands of experiments that show that that reality is best described not by a discrete 3-dimensional space and time like we interpret with our brains, but a 4D curved space-time. All right, so an even weirder space-time than we're building up to talk about so far, because so far we've mentioned curved space-time, but we're only really talking about flat space-time. So what you have to do is look at, you know, and he'll do this in the final video, sort of build up, okay, is you'll find something building up, whatchamacallit, building up a space-time interpretation of Newton's laws, and then we'll see if those are correct, or if Einstein's curved theory is correct. And experiments consistently come down on Einstein's side, but what we want to do is begin to understand one of those experiments so you can see how that works and how that actually happens. So yeah, all right, so let's get to the next one. And this will build up flat space-time and how we analyze space-time diagrams. So we'll come back at around 5:15 and look at this one. Okie dokie. So that one I bet was super confusing. Yeah? With the space-time diagrams and all the stuff? What did you guys think? Yep. All right. So it's just the way we look at, like I said, it's a way of looking at things and determining, straightness and curvedness in space-time. And that's what we're going to see as we go through. Because once we define a space-time, we have to have the machinery to talk about things as curved or straight, right? And we'll need to use our definitions of parallel to be able to tell that. As he showed you, though, it gets pretty wacky from one person's diagram to another person's diagram. You can't trust your eyes. So that makes it very confusing. And again, just the way you look at things is not intuitive, right? Again, like he says before, it's not this kind of space or this kind of time. So let me get to there's only one more video, so don't worry, we don't have a million more of these to go. You've all been good sports. So let me just get the link ready. And did anyone want me to expand or talk about anything? Again, I'll talk about what we're doing with these after we watch the last video. Okay? So thoughts, questions? I'm pretty sure your minds are all strained, but that's all right. All right. There's the link for the last video, and that one is, let me see how long it is. Okay, it's a bit of a short one, so that's good. So let's give it another 15 minutes. Let's say maybe call it an even 5:35. Okay? All right. Turn off the mic. Hopefully everyone's wrapped up. It should be interesting to see how space-time works. And we're going to what I think I'll do is we'll take our break, and then we'll so that your minds can reset, and then I want to go over the experiment from the video and describe it to you to show you the main key points, because I know Gabe talks fast. It's the host of Spacetime. And so we're going to go over that, and then we're going to talk about black holes for the rest of the time. So I don't want to take as long as a break as we usually do. I just want to give us 25 minutes. So I need to get to your guys' stuff. I wouldn't worry too much about your grades on those unless they're really bad. I'm sure my experience with this class is most students do an okay job about it, but I will be grading those soon. So I'm hopefully we'll have a better grading schedule down. So yeah, so that'll all be coming soon. But I wouldn't worry about it if I were you. So what we are going to do, I'll talk a little bit. We'll go on break. We'll come back at 5:02 and we'll talk about the activity I want you to do. I want to treat these sets of videos as an activity, which is new. So I want you to think about them, copy the links if you need to rewatch the videos, right? Watch them a couple times. And like I said, watch them with family members and people you're quarantined with, and talk about them. See if you can explain them to someone else. And if those discussions help you get a better grasp of the idea of space-time and general relativity. And then when we come back, we will discuss black holes and sort of see some cool and interesting properties about them. Okay? All right, so 5 till, we'll come back. I'm going to stop the recording and then restart the recording because that's just too long of a break.